So the concept of error is really central to the subdiscipline of analytical chemistry. And to be honest and be fair, it should be the centrality of all science and STEM. Um, Error is what makes us know whether or not the value we're reporting or the measurement we're doing has any meaning in terms of real life. Anybody can do a measurement. Anyone. Anyone can attempt to measure something, but without a framework for thinking about, discussing, reporting, and treating error, the numbers are meaningless. And I would argue that this is a significant divide in the scientific community because there are disciplines who consider less the error of their measurements, in which case reproducibility gets challenging, especially with published work. And there are disciplines who error is central to, and I would argue that it should be ubiquitous across disciplines, but it's not. So error, I think, the reason it's not always treated is because it's cumbersome to think about how error manifests in every experiment you do, and that's not really the goal of analytical chemistry, to just do everything minimizing error always. That's a waste of your time. What's a better use of your time is to know when minimizing error is worth your time, worth the energy and the resources, and knowing what measurements don't matter. And ultimately, that comes back to what is the outcome of your measurements. What do you want to do with them? And say you're doing 10 measurements of 10 different things, and then you're doing some math to compute a final value. And maybe you can do 9 of those experiments with great accuracy. And one of them, you're not going to be able to do very well. In that case, it doesn't make sense for you to do any of them well, because ultimately your final value you'll never know to greater accuracy or precision than the input or the experiment that you knew least well, right? And so the goal is to develop an intuition and framework in this class to know when is it worth it, when should you do it, and when should you not. Um, so to do that, let's talk a little bit about the difference in error and uncertainty. And in this class, they're going to be more or less the same. Uncertainty, we're going to think about as an actual computed value, whereas error, we're going to think more as a concept. And we're going to think about error in manifesting in a few different ways. So error cited is the difference between measured value and true value for a measurement. It's not often determinable because we don't really know the true value. And I mentioned this when we were talking about accuracy a couple videos ago. Um, when you're doing a measurement, especially of an unknown thing, imagine that you are an astrochemist or an astrophysicist, and you are measuring for the first time in human history the composition of a planet's surface or an atmosphere or something like that, right? There is no true value that you know of, but there is a true value in that it's a real thing, so it must have a determinate composition. So the true value is whatever the actual composition of that thing is, but by true value, it may not be known to humans yet. So error in its sort of hypothetical sense can be difficult to determine. Uncertainty, though, is a range of possible values within which the true value should lie. And so this is more of a numerical quantity that's essentially a range or a value where you can say, here's my average plus or minus my uncertainty. The true value will lie within that with some level of confidence. And that's how we're thinking about, though. So the little schematic that I have here says increasing trueness on the y-axis and increasing precision on the x-axis. This is a really standard sort of description between the difference in precision and accuracy. So in the bottom left corner, we have something that's low precision and low accuracy, meaning we have low reproducibility across measurements, and those individual measurements are far from the true value, the red bullseye. And then all the way to the right over here, we have an area where we have good clustering, meaning we're super reproducible. We do the measurement the same every time, high precision, but we are low in accuracy. And so we call that sometimes bias, or in other words, we call this, and I'll talk about this a little bit, a systematic error. where we're doing something systematically different every time, but we're doing it the same in difference every time, meaning the error that we have is roughly the same every time. We can contrast that to the top left picture, which shows when we have low precision but fairly high accuracy. And so our clustering is low, meaning we're not very reproducible, but the clustering is generally around the centroid or the true value that we know. This is a different type of error, and this is the type of error we call random, in which case it's actually not correctable. It's something that we could try our best, but the universe has built in to whatever experiment that we have for a variety of reasons we'll talk about later. And then, of course, in the top right, we have the example with high precision and high accuracy. So another way to frame that is to really subdivide error, or this big sort of hypothetical concept, into its two subcategories, one being random error and the other being systematic. And so as I sort of alluded to with the bullseye analogy, is that systematic error often manifests as a deviation from true value. So often with systematic, if you're really a systematic scientist, right, you're doing everything the same way every single time, which means you're getting on your bullseye, you're getting roughly the same result every time, but maybe that result is consistently a field or a far away from what the true value is. This is an example of systematic error, and accuracy is the proxy or the metric that tells us whether or not we have systematic error. So in order to evaluate if you have systematic error, we need to know the true value. And so, for example, maybe you do a measurement of, say, I don't know, the density of water. Right, that's kind of a boring example, but maybe you're trying to figure this out. And you systematically do a bunch of measurements, and they're all really close to each other, but they're far away from the value. But you can look up the true value, and there's no way to know the absolute true value that the universe produced for us, but there's millions of people who have measured this, so we've converged on an answer that's as true as we can get as humans. We also have national labs like the National Institute of Standards and Technology, NIST, this is up in Boulder, which it's their sole job as scientists to measure true values of lots of things, like the meter or the second or any of the units that we're used to in SI units. This is where the atomic clock exists, how we calibrate all time, which is fascinating discussion in itself. So in order to evaluate if we have systematic error, we are using accuracy as a proxy, which means we need to know a true value, which means we need to look that up or know that somehow. And there are several ways to do that. Often, if it's a measurement that lots of people have done, we can look that up. We can look it up in a published literature. We can use NIST value. But the level of trueness there, you should always know, is subjective. There's no such thing as a purely true value, because there's always going to be some error or bias introduced by the human, the measurer, because we have to construct these sort of brute force ways to do the measurement. We can never just know the value. We have to measure it somehow. So in contrast to that, we have the random error, which if we do the bullseye analogy again, as I mentioned, in that case, we could have, lots of measurements where they're clustering generally around the true value, which would be the centroid of this bullseye, but we're not very consistent in our measurements. But the consistency seems to be about the same everywhere, right? They're clustered around the centroid in a pretty consistent way, meaning they're not all skewed to the left or to the right. In that case, what we're seeing is a random type of error, and random error is really hard because random error we can't fix. No matter all the things we can try, you can imagine with systematic error, right? As long as you can identify that systematic error exists in your procedure, then there's a way, there is a mechanism by which you can remedy it. So systematic error is fixable as long as you can identify that you even have it to begin with, which means you need to have a true value to begin with. Random error, there's nothing we can do. There's a lot of examples of random error out there in measurement science. It's a whole field in and of itself. And if you go on to take an instrumental course, we'll talk about 5 or 6 different flavors of random error. I'll give you for one example. If you're doing a measurement with an electronic circuit, there is random chaos in how the electrons are bouncing around that circuit. That chaos comes from quantum mechanics, actually, and we have no control over that quantum mechanics, so there will always be some small margin of error or uncertainty associated with every electronic measurement simply based on that randomness, and we can't control it. That's the difference between random and systematic error in the types of measurements that we do. So thinking about a systematic error, another systematic error might be how we think about measuring a. So I showed this picture before, which is actually a really good illustration of systematic error. It wasn't my intention, but it's a good example, right? These eyes to the right, these could be 3 different people, right? This could be Kate, this could be Mary, and this could be I don't know, we'll say Bill. And these 3 people are all looking at exactly the same tool with exactly the same volume, but they're all looking at it slightly differently, all right? Kate's looking at it slightly higher, maybe she's taller, maybe Mary's height is right there and Bill's a little bit shorter, and they're all looking at this slightly different. So if you think about it, Bill goes through his experiments and every single time is looking at the burette from below, and Kate does this consistently from above, then Kate and Bill are systematically going to, even if they're really good in getting the same measurement every time, they're going to get a series of measurements that cluster together, but they're all systematically deviating from the true value. This is a really good example of a systematic bias in a measurement. This can manifest in virtually all measurements, right? And so as scientists, our whole goal is to do everything we can within reason and within our resources and time to identify where systematic error manifests and then try to remedy it if it's worth our while, if the answer merits that type of care. So how do we think about our errors and how they can move through a calculation? So if we do a measurement of, say, absorbance, and we want to use that absorbance to then have a calibration curve and compute a concentration of a solution, which you'll do in this class. How do we do that, right? Because there's going to be some addition, subtraction, some multiplication. All of those things are going to change the certainty or the significance of which we know that value. And so significant digits and uncertainty are absolutely related to each other. Uncertainty is really more the absolute way of thinking about significant digits. In order to do that, we need to think about uncertainty in sort of 2 categories or terms, and they're really the same thing. They're just different ways of thinking about the same type of uncertainty. So as an example, for a burette, most that you've talked about for titrations, the uncertainty is actually written on the side as 0.02 milliliters, which means every measurement you make, every time you read the volume off of that, you can then say, well, that's plus or minus 0.02 milliliters, which is an absolute uncertainty relative to that measurement. In contrast, a relative uncertainty would be a value of uncertainty that's related to the specific experiment. In other words, if we had 0.02 milliliters divided by the actual measurement maybe you made was 25.50 milliliters times 100%, that'll give you how large is this error, this 0.02, relative to the size of the measurement you make, right? Is that 1% of the measurement or is that 100% of the measurement? So relative error can be convenient in just representing how large that is. But it also becomes useful in how we treat the mathematical description of how error moves through calculations. And we call that error propagation or propagation of error. And I'm going to teach you a basic way, and the textbook uses this way too. If you go on to take physical chemistry or maybe even physics, I don't know if they do it here at CC, They'll teach you the more formal way to do this using calculus, but it's beyond the scope of this class since calculus is not required. And so error propagation is the mathematical way to treat error on measurements if and when you perform math on those measurements. So there's some rules that we're going to talk about and we'll move through. I also want to mention that when we are propagating uncertainty, we are only really thinking about random error. So when we talk about uncertainty, and I mentioned the rough definition of uncertainty at the beginning relative to error, we're thinking about uncertainty in terms of the error that we can't control. And that's really what we're going to talk about in this class in general. We'll talk about identifying systematic error, but we won't treat it through propagation of error. We're only thinking about random error. So statistically, it changes how you treat that. So we're assuming the error is random associated with the measurement. How do we treat that mathematically? I'll also say that a good proxy, statistical proxy for random error in a series of measurements, if you conduct, say, more than 3 measurements, is the standard deviation, which you've all heard about, but you may not have thought about how it fits specifically within the treatment of error. So standard deviation is actually a really good proxy for random error or uncertainty in this case. So when we use Excel to compute standard deviation, it's a reasonable approximation for uncertainty, assuming it's only random error that's contributing to that value. We'll also talk in the lab about how to compute the absolute uncertainty of a value, specifically when it comes from a calibration curve, which actually uses 2 different variables. So this gets complicated pretty fast, but this is the picture that I want you to take away with right now. Proxy, standard deviation, random error. How do we use those errors and how do we propagate them through a series of calculations if we're doing math on some numbers? So why is error propagation important? And so I want it, it'll feel abstract when you first start to think about it, but let me give you a real world example. I know you may not all be health interested or interested in health fields, but health is often a place where error is really important. We got to know it because we're ascribing some sort of diagnosis to patients, and the margin for presenting an incorrect diagnosis is low, and it can result in complications or even death of the patient. So it's really important that we have a solid construct of error when we're thinking about health. So I just tossed in this thought. So imagine you're a healthcare professional, you have a patient with kidney failure. One way to monitor the patient is through blood density, which is proportional to this stuff called hematocrit levels. So in order to measure the blood density, you got to measure the blood volume and blood mass for a sample, right? So it'd be mass per volume, just like determining density of anything. And that's a pretty easy measurement to do, right? We have a vessel where we know a determined volume, and then we can measure the mass of that thing. We divide them, we would get the overall density of that solution. But each of those measurements to construct the density calculation, there's 2 measurements, right? We're measuring both the volume and the mass of that object. So the volume itself is going to have some uncertainty, some error associated with it. That's denoted by this 0.002 milliliter value. The mass of that stuff will also, because it's a totally separate measurement, is going to have an uncertainty based on whatever balance you choose. And so here the balance, this is not a very good balance because its uncertainty is in the hundredths place. So this is probably a top loading balance. So the question is, when I take these 2 numbers and I take mass divided by volume, how well do I know that number? How do I treat these 2 errors? That's the question, and that's the importance of propagation of error. Because I'll tell you, it's not simply an addition of these 2 things, because if you think about it, these 2 values are plus and minus. They're not simply a plus or a minus, so we can't just add them. So just like sig figs, where the methodology or the rule by which we conserve significant digits depends on the mathematical operation, the same thing is true for error propagation. So if you are adding or subtracting measured values that each have their own associated error with them, then to compute the total error of the new measurement, you are going to take the first measured error squared plus the second measured error squared, and then you're going to take the square root of that. And so you're squaring and taking the root, which is because errors can be positive or negative. So we're essentially normalizing to the sign of that error. So for example, let's think about back to our sort of burette example, because it's a common piece of glassware. I've got a couple numbers here. So imagine you take an initial reading, right, which is what you would normally do when you start a titration. Even that reading, just looking at it, has an error, again, of plus or minus 0.02. That's pretty standard for most high quality volumetric glassware like a burette. And so that means our initial reading, maybe that's 0.05 milliliters plus or minus 0.02, because that's the error associated with it. And then our final reading on our burette might be 17.88. And again, it's going to have the same error because it's the same measurement, milliliters. So if we want to find how much volume was dispensed, or added in this case, into our volumetric piece of glassware, we would find the difference, right? What was the change in volume between these two? That would equate to 17.83. But what do we do with the errors? Well, our error here, this is going to be error 1, and this is going to be error 2. In this case, they're the same error because they're the same measurement. So in order to compute this, we would take this and we would say, well, the E total, or the total error in this measurement, is going to be 0.02 squared plus 0.02 squared, root of that. That's going to give me the error associated with the difference, the 17.83, which equates to plus or minus 0.3 milliliters. So this will be our final answer. Okay, so how do we think about this new sort of error propagation within the framework we already know of significant digits? Well, let's see. If we compute an error and we know that the error starts here in the hundredths place, then that means that the least significant digit that we can have in our number would also be in the hundredths place. That means we wouldn't be able to know any more digits past the hundredths place, because then the error becomes very large after that, right? So that means we know this fourth digit here with the plus or minus 0.03, right? It could be 17.80, it could be 17.86. That means this last digit, we don't know 100%, but we know it enough to consider that a significant digit. How would we have thought about sig figs in this computation? Well, it actually would have given us the same answer, right? Because the rule for addition subtraction is to preserve the least number of digits past the decimal. We've got 2 past the decimal here, 2 past the decimal here, and 2 past the decimal in our answer. So they're consistent with each other in the descriptions, but instead of simply writing it as 17.83 with nothing in terms of error, now we actually provide a range of values of where the true value should lie, which is what this uncertainty is telling us. So hopefully that makes some sense. Okay, so the table that I have here comes straight out of your textbook, Chapter 3. It's just a summary of the rules that pertain to propagation of uncertainty or error by mathematical operation. So what we just talked about was the subtraction operation, which would be, let's see, this one here. And it turns out that the addition operation is the same, and that makes sense because our Sig Fig rules are also the same for those two, so they would produce the same results. And so here, E of y being the value you're computing, that's the actual new value, is going to be the sum or the root of the squares and the sum of those individual errors, just like we did for the previous example. So for multiplication and division, which are here, you can see that it's slightly different. And in that case, we're representing this as a percent error instead of an absolute error. So this is relative, as I mentioned before, these are relative errors rather than the absolute errors that are being considered in this case. It doesn't really change that much, it's just one extra step. We have to convert absolute errors into relative errors before we compute the uncertainty. So I'll do a quick example. Okay, so let's pretend we have an operation like this. So we have three measured values. We have 1.76, we have 1.89, and we have 0.59. Those are three measurements that were done. And for whatever reason, we don't have any context here, you need to multiply by the first two and then divide the 0.59. Each one of those has an error associated with it. We'll say that's E1, E2, and E3. These could be masses, they could be volumes, whatever. They have errors associated with them. And as I mentioned, the rule for error propagation for multiplication and division is slightly different in that it requires us to have percent or relative uncertainties in that permutation. So before we do anything, in computing the error, we need to convert these absolute values. You know they're absolute because they don't have a percentage associated with them. We need to convert those into relative. So what is relative? Well, it's just the error divided by the measurement times 100%. So if I wanted to convert this one to a relative error, I would take 0.03 divided by 1.76 times 100%. That would give me percent E1. And for this one, I would take 0.02 divided by 1.89 times 100%. That's going to give me the percent E2. And this last one here, of course, is going to be 0.02 divided by 0.59 times 100, which is going to give me percent E3. That's the first thing we need to do. So go ahead and do that. And then pause the video. Make sure you get the same number as me. So I'm going to do it off camera really quick. Okay, so here's what I computed. So all I did was convert the original absolute errors into percent errors. The original measured values are still the same. A couple things that I want to mention here. So when we're talking about significant digits in this class, well, the two things I want to mention. One is each of the errors only have one digit, and that's customary. We don't really keep any digits past one digit when we're reporting errors, whether absolute or not. So that's customary, so we'll do that, and that's why these are all reported with one error, or one digit in the error. When I convert those absolute errors into relative errors, they still only have one significant digit. But you can see I wrote these out as 1 point, and then I subscripted the second digit, and I did that for each of these. The reason I do that, and you'll see me do that all the time in this class, this is the convention I use, it's also what your book Harris uses, is that most often you don't want to eliminate values beyond the point of significance because they can contribute to a rounding error. Right? If I got rid of the 7 and I just called it 1.0, that's going to manifest as a difference in the computed value. So the best way to, if you're doing a series of computations, the best way to conserve your significant digits is to only keep one digit past significance and subscript it. That tells you two things. That tells you how many digits are significant in this number. In this case, it's 1. It's the only value that's not subscripted. But it also prevents the rounding error because it keeps one digit past significance. If you keep at least one digit past significance, or only one significant or digit past significance, you will minimize your rounding error by 99.99%. So there's never a reason to keep more than one subscripted number. So that's why I have it written this way, and you'll see me write this way all the time in this class because it's pretty common as you move forward in classes. Okay, so at this point, what we have is E1 and not E1. We have our value, and then we have percent E1 here, we have percent E2 here, and we have percent E3 here. So if we want to compute the error of the new value, which would be 1.76 times 1.89 divided by 0.59, that's going to be our new calculated value. We need to set this up in the form that we have up here, right? So we'll say that the percent of the E total, in this case, or E4, doesn't matter, is going to be equal to the root of, let's see, 1 point subscript 7 squared plus 1.1 squared plus 3 point subscript 4 squared. So if we go off camera really quick and compute this, this gives us a value of 4 point subscript 0%. And so now the last thing to do is just take and compute our actual number so that we have an associated error with that. So if we do that, we get a value of 5.6, and I'm going to subscript the 4 here, and I'll tell you why. So and then I'll tack this on. So this would be plus or minus in parentheses 4.0%, meaning the error is 4% of the 5.6. That's the absolute error. So 5.6, and I subscript the 4, there's two ways to get there. We can use Sig Fig Rules to get there, or we could use the uncertainty, right? In this case, let's think about the Sig Fig Rules to begin with. So remember, Sig Fig Rules are, if you have multiplication or division, you're going to preserve the least number of digits. In this case, we have 3 sig figs, 2 sig figs, so we can only have 2 in our final answer, which we do have, 5.6, and the subscript is 4. That will always work if you want to double check your answer. The other way to know this is to think about the uncertainty just as we had done before. This should make logical sense because the uncertainty should manifest in our least significant digit, the one that's still significant, but we know the least with certainty. In order to do that, we need to convert this relative uncertainty back to an absolute uncertainty, and we do that just by multiplying the percentage by the value. So in this case, that would be 4.0% times 5.64, which gives us around 0.040 times 5.64, which equates to an absolute error of 0.2 subscript 3. So that's the true error in this number. It manifests in the tenths place, which is exactly the place of our least significant digit, consistent with the Sig Fig rules. So both of these things should always be consistent. Wherever the error manifests, in this case the error manifests in the tenths place, then that's going to be the last significant digit. We won't know anything else beyond that with significance. So hopefully that's helpful. Practice this. Takes a little bit of practice in doing, but it's pretty straightforward.